Hi, welcome to my channel. In this video, we are going to design a strap footing using Staad.Pro and Rcdc. There are a lot of people requesting me to upload a video regarding strap footing design. I am going to use a model that I used in my previous video where the topic was about eccentric footing design part 1. Strap footing is a component of building's foundation. It is usually used in conjunction with columns that are located along a building's property or lot line. Columns are typically centered on column footings, but in the conditions where columns are located directly adjacent to the property line, the column footings may be offset so that they do not encroach or trespass onto the adjacent property. This results in an eccentric load of some portions of the footing, causing it to tilt to one side. Now, if we have strap beam, this strap beam restrains the tendency of the footing to overturn by connecting it to the adjacent or nearby footings.
Okay guys, let me open my model here. In order to save money in the design, in the analysis, I modeled separately the superstructure from the substructure. Let me add a dead load here caused by soil equal to 14 kN per meter directed downward. Before proceeding to footing design, ensure that columns, grid beams, and strap beams pass the strength design, and we can double check it directly using Rcdc software. So take note, these are my strap beams down here. These are the initial sizes of my columns. So you see there is no problem with the columns. Next, let us check the strap beams and grid beams. The next step is we are going to check also the potting sizes in concentric design. Because if these are bigger in size, then we will be in big trouble if these are designed eccentrically. And probably we won't be able to design these pottings successfully. As we can see here, eccentric pottings are far bigger than the rest of the pottings. To adjust and make all of them almost equal in size with the rest of the pottings, we will apply a moment to the base of the two columns with eccentric footings. Applying a moment in that location will force the grid beams connected at the other end of the column to react together with the strap beams. Hence, load is redistributed among members like beams and columns. We will initially assume a moment value of 250 kN to both columns. Upon application, the strap beams, grid beams will react, and if the size is inadequate, the beams will fail in the design. If in case the strap beams fail, there is no need to resize to make them pass in the design. Instead, gradually increase the column size until the strap beams are okay. The strap beams don't help in shifting centroid of the structure because these are already stationary, and increasing the size will only lead to increase in potting size, which we don't like to take place. Unlike the grid beams, if the columns deflect in either way, the grid beams move simultaneously. Any movement of these members will also move the slab and the rest of the structure. In short, we apply the 250 kN to the seed columns and at the same time increase column size from, let's say, 550 by 550 mm to 600 by 600 mm for all columns, for example. Now we will exit this Staad and check again the footing dimension if changes takes place after some change in column dimension and moment application. We will confirm if strap beams and grid beams are not affected in the moment applied in the columns, though it is definite that strap beams are not affected because of column increase that we did. Okay, so everything is fine as expected. So we will now proceed to potting design. We'll go to settings. We have here 2.94, 50, then 33% for the bearing capacity increase, then 500 mm, so offset 300, 300, click OK, then OK. Load combinations. Then design. Now we can see that there is an improvement of the eccentric coatings. But we are not yet satisfied with the output, and we want to have more better size than this. We have to take note of the sizes because this will be our reference when to increase or to decrease moment, and we'll continue adjusting this moment until we are satisfied with the outcome. So what we do next is increase the moment by taking it or making it 300 kilonewton meter and compare the next result with this result that we have now. So here we will make this 300, click OK. Next, again 300, click modify, then OK. Then run analysis. Then close this file and we'll open the Rcdc. Oops, FC1 from 3 meters by 3 meters has now become 3.2 meters by 3.2 meters. So there is an increase in size. Therefore, we have to revert the moment back and lower it than the initial application. While FC2 has improved, so we will increase the moment in column C2. This is FC2. We'll edit this and increase this to 360 kilonewton meter. And this one is for FC1. And we'll decrease this to, let's say, 220 kilonewton meter, which is less than the initial moment of 250 kilonewton meter. Now FC1 has improved from 3.2 by 3.2 meters and now become 2.8 by 2.8 meters. The same thing happened to FC2. So let's further decrease moment in column 1. Let's increase the moment in column 2, hoping we will get better result than what we have now. For column 1, we will try 180, and for column 2, we will try 360. If C1 increases from 2.8 by 2.8 meters and becomes 2.85 by 2.85 meters, it would be finally better if we adjust the moment from 180 and increase it to 200, and this will be the final moment. For FC2, I think we will try 420 kilonewton meter because it has been improving until now. So increasing the moment to 420 kilonewton meter will be the final to have the best result. Okay, let's do it. Oops, I was wrong. Let's try again decreasing moment of column 2 back to 400, 380. Let's make it 380. Okay, these are our final voting sizes. I hope you like this video, and if you do, please like and share this to your friends. And please don't forget to subscribe and hit the notification bell for you to be updated. Thanks for watching and bye.